please welcome Jonathan. Jonathan is going to give a talk on relay communication services to support lunar exploration. I ask you to keep your microphone on mute until the question and answer time, and you can either post in the chat or raise your hand and I can call on you. All right, over to you, Jonathan.
Yeah, thank you. Yeah, so I'm Jonathan Friend. I'm a mission concepts engineer at Surrey Satellite Technology over here in the UK. And I'm going to be talking to you about relay communication services to support lunar exploration. So this is effectively a program that we've been working on for a number of years now in SSTL. And effectively what we're aiming to offer is a commercial relay communication service for any assets operating around the moon or on the lunar surface. So the aim of this being to help to build the parts of the necessary lunar infrastructure to enable wide-scale and sustainable lunar exploration. And to do this, we're aiming to take a stepwise approach to enable us to gradually build up capabilities and to offer services into the lunar market as the market is maturing. Okay, so it's quite an ambitious endeavour, and through this we're aiming to develop the vital service infrastructure to underpin lunar exploration and lunar science, and to provide support services to lunar assets, helping to build part of the wider lunar value chain, and setting up a viable communications business model, kickstarting this with public-private partnership collaborations. So what will this mean for the users of this service? So firstly, lower cost. So if missions want to go to the moon at the moment, an individual spacecraft will need to take all of the equipment necessary to communicate all the way back to Earth. We'll need to use sort of near Earth and deep space capable ground stations, and we'll need to buy time on those ground stations and be able to get useful data through those links. So this can be quite expensive. It can be quite, the equipment necessary can make up quite a large mass margin, which effectively is limiting the mass available for the payload, which is ultimately the purpose of the mission. So by providing the data relay services in much closer proximity to the moon, this equipment can either be reduced in size, enabling the greater mass fraction to be dedicated to the payload, or reducing the overall mass of the spacecraft, or the similar equipment could be taken, but much higher data rates could be accessed. So there are varying benefits there, but these could add up to a lower cost overall. The costs of the services are also aimed to be priced competitively. So potentially, if more data can be put through at the same cost you'd be paying for other services, that could be an overall lower cost. It could provide enhanced autonomy for rovers. So if a mission can be developed where a rover knows it's getting access to comms at quite frequent intervals, the operations could be planned in a much more autonomous way than maybe necessarily having to have a dedicated ops team planning in particular communication sessions with that rover. It could provide, as I said, enhanced data rates over direct-to-Earth communications potentially, and greater mission assurance, given that things like the geometry, where the Earth will be in maybe one position all the time. This can be good for direct Earth communications and knowing where you need to communicate, but could potentially be bad if there are problems with antenna system deployments or abstractions from local geography, things like that. Whereas a relay spacecraft could provide a variety of different geometries which would allow communications to potentially get through, which would otherwise have meant failure of mission if those communications couldn't be achieved in a timely fashion. Can provide reduced complexity. So benefits from the reduced range of the relay spacecraft could mean that link budget could be closed with much lower gain antennas, for instance. So particularly for mobile missions, such as rovers, data could still be put through to the operators using omnidirectional antennas at reasonable data rates. So the rovers wouldn't have to worry about steering antennas back to a particular vector to get those communications through. So this could add kind of a robustness to the operational approach. And the ultimate goal as well is to provide navigation services. So not having to rely on either ranging back to ground stations on Earth or purely on feature-based methods from surface operations. Okay. So why are we doing this? So we've all already heard about many of the interesting activities that in the various other talks today about what people want to do at the moon, and this interest has kind of been rekindled in the last few years with initiatives such as the Google Lunar X-Prize, the Catalyst program from NASA, and more recently the NASA programs such as Artemis and the CLPS program, as well as numerous other initiatives and other institutional programs from various agencies from around the world. There's been this renewed interest, which has meant that lots of other companies are thinking about ways to support the potential return to the moon of various robotic and eventually manned missions. So this market will be likely made up of a wide variety of capabilities of missions, from small CubeSat missions through to large human landers and everything in between. So robotic landers, rovers, impactors. And we've been doing a significant amount of work on trying to understand how this market is going to gradually be built up, and what those timeframes are, and what the various challenges are for those markets, and how technology developments will lead to those markets increasing in capability and frequency of missions and such like. So, for instance, in the 2020s, we're probably going to see the development of various technologies to enable longer missions on the lunar surface. So I think we've had in several of the talks today about the challenges of the lunar night and operating around the lunar poles, where the lunar environment can be very harsh and there's not access to sunlight for power. So we've heard about various technologies for addressing these problems. We've also heard about the key areas of scientific interest and prospecting interest. So around the poles in particular, the areas with volatiles, particularly water ice and things like that, that are potentially of interest for science and for the long-term sustainable development of the lunar surface. So to access these regions, some of which are really quite small, technologies such as precision landing will be crucial for enabling those longer duration missions initially. So targeting peaks of eternal light, or trying to land close enough to the areas of interest of those missions to be able to fulfill those missions successfully. And we've also got the potential for human operations on the surface, supported by the Gateway in the 2020s, I think, with the first landing aim for 2024. Then in the 2030s, we'd hope to see, building on these initial steps that have been taken in the 2020s timeframe, a more permanent surface infrastructure in place, longer term human habitation, progressing towards permanent human habitation of the lunar surface, and a build-up of intensity of the development work in terms of developing the protocol and technologies and capabilities to be able to take the next step for Mars exploration, but doing it in the testing ground of the lunar surface. So we've been developing an understanding of the lunar market and trying to develop tools for statistical analysis of and prediction of how we think this market can build up and in what ways, and how the capabilities will be increasing for us to address what the needs will be of these missions, and how we can build a business around delivery of the data to allow these missions to operate and effectively operate in the future. So the main first step in this program, after some initial work internally at SSTL, really came in, I think, initially 2015, when ESA released a call for ideas for commercial partnerships for exploration. So the idea that we put into this call was for lunar communications infrastructure. And we put together this idea in partnership with Goonhilly Earth Station. So they're a company who's developing commercial deep space capable ground stations in, at the moment, the UK, but with aspirations for a wider global network. So we entered a partnership with the European Space Agency in 2018, and with this partnership, each party is bringing a key set of competencies, which is allowing us to address this problem that we're trying to look at. So Surrey Satellite Technology, we are bringing the space segment. So we've been developing small spacecraft for a number of years, since the early 80s, and been working on a number of studies and to develop on these capabilities and push our competencies out to the lunar environment. Goonhilly is bringing the ground infrastructure and the ability to have a dedicated ground segment for this endeavour, and the European Space Agency is bringing the potential for extended ground segment capabilities if required, but also deep expertise that we can pull upon for helping us to properly understand this endeavour, and enabling this through fulfilling the role of an anchor customer. So in the first phase of this project, we started to do the development work For the ground segment, this meant upgrading large ground station dishes to be deep space capable. So Goonhilly have been receiving funding from the local UK governments, industry and private sector to make these upgrades, and they've been working on their dish called Goonhilly 6 to add S and X-Band capabilities for near-Earth and deep space communications, as well as the necessary upgrades to allow ranging spacecraft. This is being done in a way that it can plug into the ESA S-Track network, allowing ESA missions to be operated from this dish to extend S-Track's capabilities. SSTL has been developing the space segment side of this project. So we've been doing numerous studies and developing business cases to really flesh out the idea of how we're going to deliver these services around the moon. And we've been jointly promoting these services with GES. And ESA have been helping us along the way in this endeavour with help scrutinising the business cases that we've been developing, endorsing the services, and providing technical expertise to help with various parts of the process. So in phase 2, we're moving on to the initial service delivery. So the idea of this is we will be launching a mission called Lunar Pathfinder, which will be the first mission to provide commercial lunar data relay services. The idea with this is, as I said, to enable lower cost missions, to provide extended coverage on of the moon, so providing coverage for the whole lunar surface with coverage of the far side and the poles. Pathfinder will be operating in a highly elliptical lunar frozen orbit, which will allow it to provide long duration coverage of the southern hemisphere of the moon, enabling it to provide long duration accesses to the lunar poles. Other areas of the lunar surface in the northern hemisphere will receive coverage from the spacecraft as well for shorter durations, but due to the reduced range, will be able to provide higher data rates during these periods, which partially compensates for that fact. So another key aspect of this mission for users will be that there'll be increased availability over a lot of other direct-to-Earth communication solutions. So particularly where the networks such as S-Track and the Deep Space Network from NASA certainly have the capabilities to provide comms for various missions on the lunar near side, parts of the lunar poles and lunar orbit. These networks are very oversubscribed with numerous missions from around the solar system. So getting substantial amounts of time on these services will be challenging. So as we are providing the service with a dedicated ground segment, we'll be able to provide longer durations for communications to these smaller assets, which would otherwise be taking up a lot of time for getting reasonably low amounts of data back to the Earth. So recently, ESA and SSTL signed a commercial partnership agreement for Lunar Pathfinder communication services. So ESA will be using a certain amount of these services for a certain period during the phase 2 of this program. We'll also be investigating the first use of GNSS receivers around the lunar environment as well, in support of an ESA program, potentially. So the next step in this program will be to enhance these services that we'll be developing for with the Lunar Pathfinder in launching a full constellation, which will enable much greater coverage of the lunar surface and additional communications channels and bands, and much increased data rates and overall greater data backhaul to the Earth. Another key added advantage of this system will be the provision of navigation services. So this will enable greater mission planning, provide greater safety and accuracy for landing spacecraft on the lunar surface, increased autonomy of surface missions and orbital missions to plan out operations. And this will provide greater mission assurance with numerous routes for missions to communicate back to the Earth. So our end goal is basically enabling the exploration infrastructure for your mission. So the key benefits will be high availability, high data return, improving the science return of missions, accurate navigation to enable in situ resource utilization, providing proving ground for the solar system communications infrastructure, and reducing the burden on institutional networks such as the DSN and S-Track. The aim of this endeavour is to provide regular opportunities for science and exploration, capacity building, cooperation, and education and inspiration, with the greater amount of access and utility of the lunar missions that will be sent to the moon. Effectively, everyone wins by enabling greater use of each of these missions, providing more science, more pictures, more videos of operations on the lunar surface will really enable the engagement of the public to a much greater degree. And the ability to support diverse applications, so really utilizing the lunar environment for science and exploitation. So really getting the most utility we can out of the missions that we want to send. Okay, and so the ESA delegates are voted, industry is ready, and it's up to you to start using these services. And with that, I'd like to hand over to questions. Thanks.
Great, thank you, Jonathan. All right, let's see. Yeah. We do have someone from chat. Calvin, did you want to ask it yourself?
Yeah, if you don't mind. Jonathan, I'm an amateur radio operator, so I was particularly interested to see overlap with your Moonlink UHF frequency range, 435 to 450 in your phase 2. That overlaps with the allocations to the amateur radio in all IARU regions on Earth. So all the way around the world, we're using those frequencies. Did you plan to avoid disrupting somehow by doing linking from, I'm guessing, a satellite, maybe in orbit or at a Lagrange point near the moon without disrupting Earth communications?
So the UHF we're looking at using is in bands that are allocated for use around the moon and Mars. They're the opposite way around at the moon and Mars, so they don't interfere. So these communications will be just from the lunar surface up to the Lunar Pathfinder and the subsequent missions as well. So the link back to Earth will just be an X-band.
Okay,
Yeah.
thank you.
Okay.
Any other questions? All right. Well, we're close to the end of the allocated time anyway, so why don't we wrap it up? And I'll see you all in another session.
Excellent.
Right.
Oh,
Thanks,
thank you very
Jonathan.
much. Yeah, thank you.